I also would like to actually start with expressing my deep admiration and gratitude to you, Tony. That many years ago, let me see, I have here a picture. I think it doesn't work. Yeah. My connection to Tony was that I was a postdoc here in 1989 to 91. And I came here because I went to a conference in Varena, and Tony gave a lecture series on macroscopic quantum tunneling and coherence. Everybody else was talking about the high TC. It was a very exciting time. But I was most fascinated actually by Tony's talk. And I thought, I have to go to Tony. Yeah, exactly. Exactly, yes. And so I wrote to Tony, and at that time, you write letters, they went by mail, and it took a couple of weeks or months, and the letter came back by Tony. I opened it, and it was handwritten. And I stared at it, and it took me literally a week to figure out whether I can go or not. If you have ever seen how Tony writes, it's a line with fluctuations, and one has to get used to learning from the noise. So it is, great honor for me, because you have influenced actually almost everything which I'm doing now. What I learned from you when I was here, and the impact it had on my entire career. I should also say, well, unfortunately, this thing doesn't work. Now. I should also thank Paul. He's, the first director, I understand, from the center here. And when I came, Paul took care of me, and we had a fantastic time. We had an office next to Eduardo, which was also fantastic. I remember we worked late night, midnight. You remember the noise? And people were thinking, what kind of noise is on the wall? We go and check, and Eduardo, after midnight, writing on the blackboard, hammering. You were there, and you were alone in there, hammering on the blackboard. And you were wondering, what are you doing? I said, I write my book. Here's the calculation, and I go in the computer and write it in and wipe it out, and the next one. So this was, great. We started to do work there on Berry phase and spin textures, with Paul, and it's still one of my favorite works. And I moved on. Schrödinger cats was very interesting to me in domain walls. And I mentioned this work because I had, after I left Urbana, many discussions with Tony. And you might remember or not, over months and months we had exchange almost daily via email about the interpretation of this kind of proposal which we had. And this was the time when I deeply started to understand what coherence and superposition is. And this has served to me for my entire career, and I'm still owing actually Tony a bottle of wine, because he put the bet on it that no experimentalist will ever do the experiment. And I'm still working on experimentalists. I have now a bunch who are very much interested, because it's very difficult, but I think it will come, Tony. And next time, when I come, either I bring the bottle or we share one. And I moved on then to smaller systems, spin qubits, which also require a lot of coherence and superposition. And this is, central topic of Tony. I had many inspiring discussions and meetings with Tony, but we didn't publish together for many years. Which was kind of surprising, because in our work, which we did, Paul, Tony had a lot of input, and he could have been first also, but he said, you young guys, this is to you. And later we had one paper, and I mentioned this paper because it's the fastest PRL I ever had. This is a record, really. It's submission to appearing in print 6 weeks. I mean, these days it takes 6 weeks before they send it out, right? And it's an extension on Mermin-Wagner's theorem, and I think it's a nice piece of work, and I'm very grateful to Tony that he pushed me to look into this more carefully. Okay, good. Well, and then before I actually come to my talk, resolution is very bad. I was totally fascinated now by the previous talk. Where is he? Yeah, I think this was fantastic. We had a paper 2015 where we actually showed that on a Kagome lattice you can implement the non-abelian topological quantum computing, fault tolerant. You can do error correction and everything in there. And now seeing, that you have these capabilities, I'm totally amazed. I think this here is actually not much more difficult a system than you consider. It's a Kagomir lattice, and on each side, you have 2 spin 1/2. You can couple them and go then to a Z4 parafermion. And this Z4 parafermion, by lattice surgery, we showed that you can do actually everything in there. So I just wanted to bring this to your attention. It's fascinating. Now, I go to the actual topic of my talk, and I also chose this here. It's a rather simple subject at this point. What I've heard here, there will be lots of pictures, but because I knew that Michel will be here, and I understand that Michel is also moving now a little bit, into the hybrid systems, superconducting, semiconducting systems. I thought there's a good opportunity for me to advertise this a little bit. Now, before saying this, I should say I'm from Switzerland, small country. We also actually are gotten interested in quantum computing. We have our national center, and the national center has its leading house here in Basel at my university, and we collaborate very intensely with IBM in Zurich and ETH and EPFL. So it includes actually all of Switzerland, but our main partner is IBM, and we do their spin qubit, semiconductor-based quantum computing schemes, platforms. And it's kind of secret for IBM. They are not really allowed to announce this openly, because also they have superconducting qubits, and they are worried when a customer has to pay now 30 or 50 million for a machine while they are working on alternative platforms. But it's a lot of fun, and I will tell you now a little bit about where things are. So from my point of view, front runners for quantum computers are spin qubits in semiconductors, and the other ones you have heard. It's actually a very special pleasure for me to say this here in Urbana, because semiconductor physics, transistors, and so forth are a very important part of the history. And I show now, let me see here, some current state of the art devices. So we had a proposal many years ago, David DiVincenzo and myself, a very crappy picture here. And this is now what came out 20, 30 years after that. And there are many, many different labs with different platforms of semiconductor-based qubits. For example, this one here is essentially a transistor. A transistor as invented by Bardeen, which is rewired and can work as a spin qubit. And that is something which has made a breakthrough in the field, because now also the engineering departments, they can think about to work with these systems and not really reinventing everything, especially using CMOS technology. The different approaches here, they are kind of separated, let's say, in 3 lines, depending on how you control the spin. It's very difficult to think of a control of a single spin which is scalable. And if you want to do this with a magnetic field, then basically you have no chance. The magnetic field is everywhere. It's very difficult to have this locally. So the idea is to have control electrically, and electrically, for example, you can achieve if you have variances in the G factor, and if G factor can be controlled by electric gates, for example. Or if you apply micromagnets on top of your system, this is something which you can see here. So you have a magnet and provides a magnetic field gradient, and Zeeman splitting from one dot to the next is different. And this allows then a separate addressability. Probably the latest development, I think is the most promising one, is the one which is based on holes and not on electrons. And holes are valence band objects which have a lot of spin-orbit interaction in there. And that means if you can control electrically the orbit, you get access to the spin degree of freedom. So the game here is to understand the hole physics and control electrically with magnetic field, with growth direction, and so forth, the access to these systems. Just to give you an impression. So there is a very recent strong development in new materials, very old ones, germanium, and germanium comes now in a very pure fashion. Mean free path now in the latest type of growth is more than 20 micrometer. And there are many different forms which you can get out of this system. So you can get it in bulk. You can get planar heterostructure. It's a two-dimensional whole gas, like in two-dimensional electron gases. hot wires, you get circular wires with a core of germanium, shell of silicon, and so forth. And they all have different band structures because of confinement, quantum confinement, and gives a lot of different physics. Resolution is not so good here. So basically, heavy hole and light hole here are completely mixed. You can unmix it. When you squeeze it in 2D, you have the mostly heavy holes. This is very good for coherence. This is our hot wires where you get subbands, and then you get further angular momentum conservation, which you can use then to quantify your levels here. And these systems, they are in detail, band structure, also free kind of electron, but band structure theory quite complicated to calculate and to determine. And basically the tools one uses is let's say for this part here, Luttinger liquid Hamiltonian 4x4, maybe the off split band here, but quite often one has to use actually even the conduction bands to get full understanding. So we do 14 band types of calculations in K.P. Approach. So here's an example. If you want to know or understand how a quantum dot behaves in the presence of charge fluctuations, because if you can control the spin by electric fields, then also the environment, which has charge noise, can affect the system. And it's very important to understand that how you can actually turn on and off this coupling, and this is possible. For this, as I said, one has to do a lot of calculation. Here's a paper which we published last year. It took 4 years of a postdoc's life to calculate the downfolding of all these terms, getting band warping terms and so forth. And in the end, the only thing you want to know is how the G-tensor gets modified by orbital effects, by fluctuations which go into the K momentum here and then end up at this point. And then from this, you can get the dephasing time. And the dephasing time depends then on the electric field, for example, which you can apply across your sample here. The upshot of this is that you not only get numbers, but you get also understanding of what is an optimization in terms of prolonged coherence time. So here's the result of the calculation. So this is the angle of the magnetic field encloses with the axis of the quantum dot here in this structure and the applied electric field. If you apply moderate electric fields, millivolts per micrometer, and you go to this perpendicular configuration as is shown here with 0 angle, then your T2 time can shoot up by 3 or 4 orders of magnitude. And this is what we call sweet spots. And since we predicted this, there are now many, many labs which have observed this. And this is something which allows you then basically to go into the sweet spots where the coupling between the, basically the spin-orbit coupling can be turned off. It's like a switch. And they do this by separation of heavy holes and light holes and other band contributions. Just to give you an idea, best fidelity, which one can achieve now, is from the Delft lab. They reach 4 nines. It's very hard to read here. So for example, this is a 2-dimensional whole gas, and with gates you define 4 dots in here and do random benchmarking. So apply a sequence of gates, and then look how well you can cover the Bloch sphere, and the fidelity measure then gives you understanding what the quality is. And so 3 of them have 2 nines. I think 2 of them 2 nines. I cannot see. It's very bad resolution. Sorry. And 1 of them has 4 nines. But it's very impressive. This means error threshold has been achieved. Now, I should also say, in this field, the game is not so much just to add up qubits. Because first one would like to understand, does one have a situation one can fully control and can see a way how to scale? Because scalability in the end, going up to, let's say, 100 million qubits is not so scary for this industry. Because a chip in this computer has by now 100 billion transistors. And it's the same size of object we are talking about. It's the wiring in the end, which is different. And but there are quite good ideas how to do this. Okay, so now I zoom in a little bit more on my actual part topic here, superconducting qubits combined with semiconductor spin qubits. So we have superconducting qubits, so the Google AI chip here, for example, I think I should also advertise Intel has now a chip out there with 12 spin qubits. That's pretty good. This is the only thing actually you can see about that. They have no papers, no specification. If you have access to some national lab here in the States, Charlie Tahan, you can get access to a chip like this, but not everyone can. But it's out, and it's, I hear it's very good. So this has been released this summer. Now, how can we bring these two things together? And there's actually already quite some development in the field. For example, topological qubits based in semiconductors. So the Microsoft quantum approach is a superconductor inducing a proximity effect in the semiconductor, two-dimensional electron gas here. We have one expert from Microsoft working on this. There are now also attempts to build up Kitaev chains based on such hybrid structures. This is from the Delft lab, Leo Cohnhoven, just kind of the first type of proto-Majorana or poor man's Majorana they established. Another hybrid system is a superconducting cavity which couples two quantum dots. This from Jason Petta's lab here, for example. And this one is the one which I come closest now in my talk, and this is Andreev qubit. There is a picture from Michel Devoray's group, which they published this year. So an Andreev qubit is an Andreev state. An Andreev state is basically a bound state, and you can get bound states either by quantum dots, by gates, or by a gap of a superconductor which surrounds a normal region. And these Andreev bound states, they become very interesting in the semiconductor. So in the semiconductor, you can get Andreev bound states easily by proximatizing a semiconductor. And then here it's all superconducting under the superconducting metal gate here. Then in the normal region of the semiconductor, you can have an Andreev bound state. What is new compared to metallic system is that spin-orbit interaction can play a very important role. And then the Andreev bound state has very interesting behavior. Here, just one example, which I find very instructive. So here you have a nanowire on top, superconducting S-wave, let's say, which induces proximity gap in the nanowire. This by itself, this statement requires a lot of work because the proximity effect is a very subtle effect and can do a lot to the semiconductor. But let's assume we have a description like this Hamiltonian here, and let's assume we have then some change of masses in this direction. We have spin-orbit interaction, which is a k or a derivative in x, and the spin-orbit parameter, which is non-zero in the normal region, and let's say 0 in this region. This can easily happen by the proximity effect of the superconductor, let's say. It's written down here. And for such a system, I can solve the Bogolyubov-Deschênes equation, and I'm particularly interested in what's happening at energies close to 0 of this bound state. So I find a bound state solution, and there is now a term in there which this cosine of spin orbit times the length of this normal region, and this is the spin orbit vector. The spin orbit vector tells me how strong spin orbit is. So the inverse is the length. When I move, then my spin turns. This is the spin orbit length. And the shorter it is, the stronger the spin orbit. And there is now a resonance phenomenon. If the spin orbit length, for example, just fits into this length here, then basically the system becomes independent of magnetic field. It doesn't see the magnetic field anymore because the spin semi-classically rotates. You have a one given direction of the magnetic field, and you rotate out the spin, the Zeeman term, so to speak. And you can see this here in this energy plot at this particular point, at this resonance point, that when I turn on the magnetic field, the Andreev bound state, instead of going straight, as it would go for a spin 1/2, let's say, it starts to get curved here and then stays at 0 energy. And this is exactly the same feature which you have for Majoranas, independent of magnetic field. And this is what people then measure in a device, for example, and say, I have a Majorana because I have a 0 bias peak. But it's actually just a feature of an ordinary Andreev bound state combined with a spin orbit interaction. just as a caveat, with these Andreev bound states, you can also mimic other properties which are deemed to be a kind of smoking gun, and this is the closing and reopening of the gap. For example, if you have Andreev bound states which overlap, so you have a few in a wire, they overlap, they form a band, so that the left and right end can talk to each other. You get non-local responses, and this is what is measured then in non-local conductance measurements. So these are simulations, and they show then a closing and reopening of a gap, but it has nothing to do with the gap age. It's just a bunch of Andreev bound states which follow the magnetic field. This kind of model passes the so-called gap protocol, topological gap protocol of Microsoft. And since we have said that, you get a lot of heat from Microsoft. You can read comments on the archive, which is replies. Okay, so now Andreev qubits, again, you know, it's a subgap state here. But if you don't do anything more, we have actually 4 possibilities. It can be empty. I can put 2 electrons in there, or an up or a down. And I can also consider now qubits in terms of 0 and 2, for example, or up and down. And this corresponds then to the parity of the state. So if I want to fix the parity, I need to do something. For example, apply a gate such that I have charging energy in my system. And then I can tune to a parity sector, for example, to the odd parity sector. And this is what I'm focusing now. This is what we would call then a Andreev or a superconducting spin qubit. Essentially, it's a confinement like in a quantum dot, but you get additional access now by the superconductor, especially when the leads are very open. If the leads are not open, you have weak tunneling. One can describe the system very nicely. This is what I do now in the following few minutes. It's very simple physics, but I find it very beautiful. So here is a setup. I have a double dot. These 2 dots are not coupled directly. They are coupled to a right superconductor and a left superconductor, like in this kind of Aronoff-Bohm loop here. And there's a phase difference between right and left. And one can analyze this system in perturbation expansion. So here's the Hamiltonian of each dot. It's a level epsilon detuned, counted from the chemical potential of the superconductor, Coulomb charging energy on each dot, such that I can control whether I have a single or double occupancy. And then tunneling between the superconductor and the dot in this kind of loop. And the superconductor, let's assume an S-wave superconductor with a singlet type of pairing. Then I have several processes which are possible. The lowest order contribution comes from a 4th order process. For example, I go from a superconductor. Well, a superconductor, here's a singlet. I go with an upspin onto this dot, move on. Second one step, I come with the second spin in, move on, bring 2 electrons or the singlet from the left or from the right side to the left side. I can also split, and this is the most interesting process. This is what we call crossed Andreev type of coupling. So that means one spin of the singlet of the Cooper pair goes, let's say, the lower branch, and the other one the upper branch. And this induces now correlations. This induces correlations between these 2 spins. So basically, I pull out the Cooper pair into my dots and see then how the spin react to this. And so I can calculate then the effective Hamiltonian, and indeed I end up then with an additional term, Josephson coupling term, which describes a spin-spin coupling between the spins in each dot. So the dots are not coupled directly to each other, but via the superconductor. And why is it interesting? Well, actually, you know, just as a side remark, this is also a way, for example, to find out what type of spin ordering you have in your superconductor. So you get a certain spin ordering and a certain prefactor here, depending whether it is a singlet, a triplet, or other pairing. So this could also be a way actually to test the order of a superconductor. You don't know exactly what it is. So one doesn't really need for this crossed Andreev pairing that I have 2 superconductors, but if I have 2, I can actually make use of the phase difference. And this allows to tune the coupling. So let's say here the term again is written down, and this effective exchange coupling has a very interesting dependence on the distance. So here I just pull it's the same system, pull them apart, and I have now a distance, let's say, between the two dots, which goes, so from superconductor, I'm not going from one point, but I go from this point. So there is a certain separation which I need to take into account. And this just tells us that I can only have this crossed Andreev pair coupling if the distance is smaller than the coherence length of my superconductor. If the superconductor is too wide, then it will not see it. Okay, so I can also now add a spin-orbit interaction to the system, and I get an additional tuning parameter. Let me just flash here the results. Now, no Zeeman term applied, and I still have time reversal symmetry broken because of the phase difference of the superconductor, and this leads to a Zeeman splitting with opposite signs at the two spins. I get an Ising and I get an XY and the Cheloshinsky-Moria type of interaction. But the nice thing now is that all these coupling constants depend on the spin-orbit interaction alpha here. It's the same Rashba as before, and the phase difference between the two superconductors phi. And here's a plot of this. And what this shows is that when we tune the phase difference between the two superconductors, and we can even tune it to a value which corresponds to some fixed value of the spin orbit, then all the other terms here, this one, except the Ising, go to 0. This is very nice. So I can just tune with the phase difference. And I get Ising interaction. If I get Ising interaction, let me just flip this. If I get Ising interaction, I get immediately a controlled phase flip. So I get a gate, which I basically can control and get very high fidelity. There's no fine tuning needed. It's just, let's say there's some Rashba coupling you don't know is given, but with the flux you can find this value and tune to such a term. This kind of scheme can be extended. I'm saying not much here. I can talk about this later then if you ask. But you can also scale it up to an entire surface code structure. Now I want to kind of generalize this to a further qubit. So qubits can not only be spin 1/2 in spin qubit business. You can form any type of qubits with 2, 3, 4 spins. Let's say with 2 spins, you can form a singlet triplet qubit. So you have 4 states. You pick, let's say, these 2 Bell states here, T0 and the singlet state. And that's a very good qubit because you can do this in very low magnetic field. And if you want to do this with superconductor, you want to avoid large magnetic fields. Therefore, that's a very useful candidate. Is it possible? Yes. If you want to go to these systems, you also should go to germanium. This is something I have to say, to Michel. So if you use 3-5 materials, you cannot do really good spin physics. It's because of the nuclear spins, and the coherence time will not be long. And germanium made very great progress now. You can proximitize germanium 2-dimensional whole gases with a superconductor on top of it. Get very nice hard gaps, has been demonstrated experimentally. It's, I think, something which can be done. There's quite some history working with singlet triplet qubits. People tried to couple them over many years. So, for example, here's a setup from Amir Jacobi's experiment many years ago. They could see some coupling, but could not get to the gates. They could not make a gate. And the reason is you need to perform, when you have capacitive coupling between the two, very large dipole moments. When you have large dipole moments, the noise also couples to the system very strongly and destroys then immediately coherence. So you see coupling, but you see no coherence. And it doesn't work. Now, well, people had strategies to kind of going around. And the proposal now is to use again this crossed Andreev process to couple. So here I have now a double dot on this side, a double dot on this side, and the inner dots here closest to the superconductor, they couple via crossed Andreev. I go through the calculation again, and let me skip that. I need spin orbit axis versus direction of magnetic field plays a very important role. I get again this Cooper pair kind of going out, in and out. and that should lead then to coupling. And just during the time when we were writing this up, there was a very nice experiment coming out from Delft, where essentially they did that. So here's a nanowire with dots, and these dots, they are coupled essentially in this crossed Andreev way. And they, in addition, had also elastic co-tunneling, and what the goal was there is getting a proto-Majorana. So with this approach, you can then also form an Andreev bound state, which is delocalized. You have one part of it on the left side, the other part on the right side, and you can tune this energy to 0. So in principle, a Majorana has been kind of implemented here. Of course, it's not topological. I mean, it's it's not separated, but it sits at 0 energy and has wave function which is partially separated. That's a very nice experiment. But anyway, going on, it's the story here. You get, so here actually the difference is that we go away from this elastic co-tunneling, and Coulomb interaction plays here an important role to get the coupling between the spins. And again, we find a kind of sweet spot that as a function of the superconducting flux, you can tune the coupling, and the coupling then leads to an effective Hamiltonian, which is again of Ising type, and get very high control over these two singlet triplet qubits. So just to show that you get very high fidelity, basically no fine tuning is needed, and the value is 4 nines with tuning only via the superconducting phase difference. Okay, good. So I think I rushed a little bit at the end. I'm at the end of my talk, and I just want to say thank you again, Tony, for everything I have learned from you, and I'm very grateful, and congratulations to you and your center.
Good question. Do you have any concern, or how do you deal with spatial variations and spin-over coupling? Obviously, under this numbers will be different, where some are exposed and the confinement data come back. So I'm just curious.
Yeah. So you mean in the calculation?
Yeah.
Yeah. Okay. I mean, yeah.
Spin-over coupling is not one parameter.
Yes, exactly. So it, there is kind of, in the simple model is an abrupt change of the spin orbit. So it goes to 0 under the superconductor because of metallization effect, for example. If you have strong coupling, so if you have epitaxial growth of the metal on the semiconductor, it changes the spin orbit interaction very strongly. So this we know, and that, it's a model assumption. And then for this case, it's solved. Yeah. Yeah.
Yeah. Okay. So again, totally ignorant question here, but semiconductors are multiple trillions of dollars. Spins are obvious qubits. Why isn't it clear that that's the winner, and how come that hasn't? What are the barriers?
Yeah. I mean, that's a question which I get very often, and I would love to pass it on. Well, I mean, the answer is I gave it actually during my talk. The industry and also the labs, they are not interested yet to going to larger numbers, because once you know how to handle 4 or 4x4 arrays completely, you can scale up. That's the idea. I'm not saying you can, but yeah.
It's not a simple extension.
No. You need to show, that you have a scheme scalable. Yeah. Well, okay. I mean, I showed you the many different spin qubits, right? And this is the big difference, let's say, to superconducting qubits, that the community has not decided yet which one is the best. And, these are all within silicon and germanium. There are holes, there are, P's, there are N's, they are grown on the surfaces, they are grown in different geometries, and, each one has its favorite.
I understand, but you have this multi-trillion-dollar.
Yeah.